Alrighty, let's go ahead and start on 11.4, which is the comparison test, or comparison tests, plural. There's two of them. There's one that sometimes is called the direct comparison test because there's no sort of in between. You're basically directly comparing one series with another. Oftentimes, a series is given to you, and it does not actually, it isn't really straightforward. Well, let's go ahead and let's look at 1 over n squared plus 1. Now, and the great thing about these tests is that oftentimes more than one will work. So we could actually use the integral test for this particular one, okay? But what we're going to do instead is we're going to say, now that's kind of similar to 1 over n squared, right? Now I know that this is a convergent p-series. Now what must the relationship be between this and this in order for me to know something significant about this, okay? And here's where the direct comparison test comes in. If you can say for sure that this series is smaller than this series at every point, then if it's smaller than a convergent series, it's convergent. How could it be otherwise, right? So if a series is smaller on every member of the domain, or the interval, whatever you want to call it, if this is smaller than that and that is convergent, then smaller than convergent is convergent, okay? And here's the thing, this actually is always smaller than 1 over n squared because a larger denominator is one way in which you make a ratio smaller. Larger the denominator, the smaller the value. And since that is always, this denominator is always going to be one larger than this denominator, I know that this quantity is always going to be smaller, okay? I mean, another way you could say it is n squared plus 1 is always larger than n, so basically then when you flip it over, it winds up being the opposite relationship, okay? And so it works the other way too. If you just need to find something that is a little bit larger than a known divergence series, and let's look at an example of that. So we have 3 to the n over 2 to the n minus 1. Well, I know that that is awfully close to that. This is a known divergent geometric series, right? Because the absolute value of r is greater than 1. It's 3/2, it's 1.5, it's greater. It's going to make each term 1.5 times the magnitude of the previous term. And if the terms are getting larger as you keep adding them out to infinity, there's no way that it can converge. So we know that for all positive n, that is going to be a divergent geometric series. Well, is this always larger than that for all n? And it is, because again, one way in which you make a ratio larger is to make its denominator smaller. And if you subtract 1, you are making the denominator smaller. Are these equal? No. This is going to be larger, right? This is larger than this because this has a smaller denominator than this. So if this is larger, because you've just substantiated that, if this is larger than a divergent series, then it is also divergent, okay? Well, just very quickly, let's go ahead and see the way that your book actually basically explains it. It says, suppose, and let me see if I can actually, zoom in on this. Okay, there we go. That's a good one. Suppose that sigma of A sub n and sigma of B sub n are series with positive terms. If B sub n is convergent and A sub n is always less than B sub n for all n, then A sub n has to be convergent as well. And basically the opposite logic works for the divergent. If B sub n is divergent and A sub n is always larger than it for all n, then A sub n also has to be divergent. Okay? Let's go ahead and let's work through a couple more examples in order to sort of solidify that. Let's take the zoom off. Okay. Alrighty. Well, let's go ahead, and we know sigma n is equal to 1 to infinity of 1 over 3n squared plus 2. Well, we happen to know what? We happen to know that 1 over n squared is what? Well, it's convergent, right? This is convergent p-series, okay? And we know that 1 over 3n squared, because it doesn't matter what constant is out in front of here, we know that c times sigma n is equal to 1 to infinity of 1 over n squared is convergent. So that means that if this is convergent, then the specific for a specific constant out in front, that is convergent. So if this is convergent, I simply need to show that this is smaller for all n. And it's the same logic as the first one that we did. You're making the denominator larger. If you're making the denominator larger, okay, then basically what happens is you just need to state, this is smaller than this for all n. And if that's the case, if this is smaller than a convergent series, then it is convergent by direct comparison. Okay? Well, let's go ahead and do another one. Okay? How about is that convergent or is that divergent? Well, here's the thing. I happen to know that factorial increases faster than exponential, which increases faster than polynomial. So my first guess is that yes, not only is this convergent, it's very, very, very convergent. Okay? But here's the thing. I know that when I actually start listing those out, and remember 0 factorial is 1 by definition. That's 1 plus 1 plus 1/2 plus 1/6 plus 1/24 plus 1/120th. Well, let's go and compare it to something that we know is convergent. How about 1 over n squared? Well, that's 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus 1 over 36 plus . Now it takes a while, but basically starting right here, okay, basically starting right there, these are going to be much, much smaller than these. I mean, the next one here in the factorial is 1 over 720, whereas this is 1 over 49, right? So you could actually just sort of, basically you need to remember that if you have terms out here, these are finite. So you can actually string this out and say, 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus sigma n is equal to, instead of 0, 0, I guess it was 0 plus. So I guess it winds up being here instead of here, right? So this is 0 plus 1, 2, 3, 4, 5, or 5 to infinity of 1 over n squared. So you wind up comparing not n is equal to 0 of 1 over n squared to n okay, you wind up not comparing these. You wind up comparing instead n is equal to 5 to infinity of 1 over n squared to n is equal to 5 to infinity of 1 over. So factorial and squared, you wind up comparing these. Well, that's just as legitimate because in front of both of these are simply 5 terms that are finite. Okay? So basically you wind up if this is convergent, and we know that it is by p-series, then this is convergent, and this plus a finite number of constants out in front is also convergent. So that took a little bit more energy and a little bit more finagling in order to actually do the comparison, but indeed it worked out. Okay? Now, that is the direct comparison. So really it's just brute force, okay? Well, let's go ahead and do one more, and we'll just relegate the limit comparison to the second video. So I have natural log natural log n over n plus 1. Okay. Well, here's the thing. We're going to go ahead and compare it to 1 over n plus 1. Now we happen to know that this is convergent for the same reason that this is divergent for the same reason that 1 over n is divergent. Because if you were to do the integral test, this would be divergent not by p-series, but by integral test, right? Because it's going to wind up being the natural log of n plus 1, and natural log functions increase, however slowly, off to infinity. So this is divergent by the integral test. And if this is divergent, we happen to know that natural log of n over n plus 1 and its relationship to n plus 1, all you need is you just need to get beyond e. The moment that you get beyond e as an input, natural log 1 is going to be greater. So if this is greater for all n greater than e, then really, just like last time, you just have to finagle it. Instead of n is equal to 2 to infinity, you just have to put one constant out in front and redefine it at n is equal to 3 to infinity, because 3 is the first integer beyond e. Okay? So basically you just redefine it and you wind up getting natural log 2 over 3 plus n is equal to 3 to infinity of natural log n over n plus 1. Okay, and you need to compare that, you need to compare this to n is equal to 3 to infinity of 1 over n plus 1. This is divergent. This is divergent. Divergent plus a constant is still divergent. So it is divergent by direct comparison. And then at that point, I think we've done about 5 examples of direct comparison. It really does wind up being very, very straightforward. You just have to sort of hone your skills in terms of what do I need to compare this to? What is my hunch? Is my hunch that it's divergent? Is my hunch that it's convergent? Go with that hunch, and then if it doesn't work out, either use a different test or find another series to compare it to in order to arrive at your answer. That brings us to the end of our first video on comparison. In the next video, we will deal with limit comparison test, which again is related, and we'll sort of hash that out, and then we'll move on to the next one, which is 11.5 and the alternating series tests. So have that to look forward to. As always, please email me with any questions that you might have, and I will try and clarify any misunderstandings that are lingering. Bye now.